Well, hello there, my friends. I am coming to you recording from my very messy craft room, as you can see, and my friend Teddy. Teddy, say hi. Can you say hi to the kids? Yes, there's our dog Teddy. So now you have met Ted. Well, now that you've met Teddy, let's talk about classroom expectations. First of all, this is college chemistry. You can co-enroll in JUCO, and hopefully Mrs. Etherton's been in to talk to you about this last week, but you can co-enroll and earn college credit. Now, why would you want to do that? Well, if you are going to be a non-science major, like a psychology major or a English major, you probably have to have a lab science. And what better way to get lab science credit than with me? Because you know I will take care of you. Now, given that, it is a college class. We are going to treat it like a college class. All right? You all have been in school for 12 and 13 years, depending on how old you are. So you know what works for you, and you know what's expected. None of this is new. I'm not going to read this to you. I do want to pull down here and talk about grades, though. So, well, let's start at the top. My Twitter is @jbushchemteach. I try to post pictures of labs and things like that, stuff that we're doing in class. I do have a remind. This works great, especially if second hour does a worksheet and third hour we run out of time and don't get to it. I can send out a message and say, hey, second hour, you don't have to do that worksheet. Or I can send out a message, hey, don't forget we have a quiz tomorrow. Don't forget your lab is tomorrow. And it's a way that you can contact me easily. So it works really well. So I highly urge you to get on and sign on to the remind. Google Classroom. I'm going to try Google Classroom this year. I've been messing with it a little bit tonight here at home. I'm kind of getting the hang of it. Some of you are going to be able to do it better than me, and if that's the case, I may ask for help. But I've always used Moodle before, but we're going to give it a go. The Google Classroom code is PPB. P as in Paul, P as in Paul, B as in ball, 7246. I did not choose that. Google did. And then I have a website that has lots of resources on it that you can look up. There's videos that you can watch. There's notes. Lots of good information. All right. Like I said, you know expectations. You can read through this on your own. Required materials, again, you know what works for you. If the 3-ring binder doesn't work for you and something else works better, I'm okay with that. If shoving all your papers in the bottom of your backpack is what works best, I'm going to guess that might not really be true. But I'm always willing to spend a half time with you dumping out your backpack and sorting through things. Okay, you're also going to need a lab notebook. We'll use the 50-page one, so it's only $10. You can bring that money in. You may have already brought it in and gotten your lab notebook by now. We aren't going to be using it quite yet. Grading. This is the part I do want to address. Tests are 40% of your grade. Quizzes, it says about 20%, scratch out the word about. They're 20%. Assignments are 10%, labs are 30%. So if you're the kind of kid that never does your homework, assignments are only 10% of the grade. Most of the grade is stuff you're doing in class. Okay, so you can get away without doing your homework. But if you don't do your homework, you're not going to do very well on the tests. And I highly recommend you do all that because, speaking of tests, it's college. There are no test retakes. It's just not going to happen. I'm sorry. I know it sucks, but that's the way it is. Okay? Grading scales listed there, makeup work, late work, etc., etc., etc. The college chem information, if you are enrolling at JUCO, is not on there. It is slightly different. College chem, you enroll in 2 courses. 124 is the lecture. It's worth 4 hours of credit. For that class, tests are 60% of that grade. The final is 20% of that grade. Quizzes are 10 and assignments are 10. The second course you enroll in is 125, which is the lab. For the labs are 50%. The lab practical that we will do second semester is 30%, and lab quizzes are 20%. So this gives you an idea of what to expect. It's graded a little bit differently for JUCO than it is for North. And then their topics for college chemistry are listed there. You'll notice the next page has signature lines. Please sign this, and that tells me that you've read this. If you haven't turned this in by the time I get back, we'll probably have to sit down and make sure that you have read it, or I may have to read it to you. Don't make me do that. And sign your printed name, okay? Because I know I can't read your handwriting, just like you probably can't read mine. Actually, mine's not too bad, but we'll get there. All right, the next section in here lists what we're going to cover for the first test. This is straight off the JUCO website, the college competencies. A lot of this stuff you've done before. All right, and really, other than the electrons, most of it you should have covered already. You should be very familiar with this. So what we're going to do now is start taking some notes, and we will be talking about measurement and metrics and things like that. All right, so let's talk about measurement. You're going to fill these notes in as we go. It's not a big deal. Mass, of course, is the amount of matter in a given object. The more matter you have, the larger the mass. This is different from weight. Weight is actually a response of mass to gravity. So if you are on a different planet, your weight is different, although your mass would stay the same. If you've taken physics, you know that weight is actually dealing with gravity and forces, and never mind. Volume is the amount of space something takes up. Last week, you talked about density. And you talked about the fact that density is the relationship of mass and volume, or that ratio of mass over volume. Length is, of course, the distance something travels. And temperature, of course, is the measure of how hot, or not how hot, how much kinetic energy an object has, the molecules have. Basically, how fast the molecules are moving. Back in the day, I loved teaching 7th graders, because 7th graders will believe anything you tell them. One time, my room the furnace had broken, and the room just kept getting colder and colder. And the kids would come in and say, "Why is it so cold?" I got tired of saying, "Because the furnace is broken." So I started making stuff up, and I told them that I was trying to make it snow. And then one of the little girls walks in the next week and says, "Did you ever get snow last week?" 7th graders will believe anything. Okay. Another thing I would do with people come in and ask me, "Why is it so cold?" Instead of saying I'm trying to make it snow, I might answer, "Because the molecules aren't moving very fast." And why is it so hot in here? Because the molecules are moving fast. That is where that comes from. All right. The unit we use to measure mass is the kilogram. Now, I know you're going, "Wait a minute, grams." Grams is, yes, that is what we usually think of. Grams are what we use, the base unit. But the kilogram is the official base unit for mass. And length, of course, is meters. Volume is not listed on here because volume is a calculated, but we use either liters or milliliters or cubic centimeters. Temperature is going to be measured in Kelvin, which is the same as Celsius, but no negative numbers. All right. Here you can see different metric system prefixes. Hopefully you all remember in middle school, King Henry died Monday drinking chocolate milk. King Henry died, if you're talking about meters, Monday drinking chocolate milk. If you're talking about liters, King Henry died lately drinking chocolate milk. If you're talking about mass, King Henry died grossly drinking chocolate milk. This is a mnemonic just to remember the basic pieces of the metric system. Metric system's great because it's really easy to convert from centimeters to meters and from meters to kilometers because you just move the decimal. You don't have to divide by 12 like if you're going feet to inches. You don't have to divide by 3 if you're going yards to feet. It's so easy. Okay? So this kilogram is 1,000. Hectogram would be 10 to the second, 100 meters or grams or liters. The decameter would be 10 meters, grams, or liters. Deci means 1/10. Centi means 1/100th. Milli means 1/1000th. So here you've got these guys explained. Okay, hecta and deca don't ever get used, which is why we just kind of ignore them. Now, we're older, we're going to learn some more. There are larger ones than a kilogram. Here we have the metric prefix scale. Each one of these lines is 10 to the third larger as you go to the left. If you go to the right, it's 10 to the third smaller. The King Henry died Monday drinking chocolate milk is right there. But we have some new ones. Mega, if kilo is 1,000, mega is 1,000,000. Giga is 1,000,000,000. Running out of zeros. And tera would be 1,000,000,000,000. You've heard those terms, gigabytes, megabytes, terabytes. Back when computers first started, we had kilobytes, and that's what we worried about, is how many kilobytes did we have back in the day when I first started teaching, when we only had one computer for the whole science department. Now, here's milli. We have 3 of these that are smaller. 10 to the third smaller. So milli is 1/1000th. Micro is 1/1,000,000th. Nano is 1/1,000,000,000th. And pico would be 1/1,000,000,000,000th. Okay? This is important. All right, you're going to need to be able to go back and forth through this system. Last year we made up a way to remember tera and giga and mega, and I can't remember what it is, so I'll have to ponder on that and get back to you. All right. Last week, when you measured, one of the things that we talked about was how to read the measurement of the graduated cylinder. It's important when you are reading a measurement that you always estimate one past the given measurement. If you think about it, when you put things onto the balance, this last digit will change. That's because the balance is actually doing the estimating for you. This is accurate to 1/10th, 1/100th is estimated. So this reading here, 12.68, has an accuracy to 1/100th. All right. Our graduated cylinder over here goes up by ones, and then each single milliliter is divided into 10. So we have tenth of a milliliter. That is the precision of the graduated cylinder to 1/10. But we can estimate to 1/100th. If this is our line, and it's not very good because it doesn't zoom in well, but if this is 8, and this is our meniscus, 8, 8.1, 8.2, you could call that 8.3. You could call it 8.29. Somebody else might say 8.28. This is the estimated value. That's your value. So you and your lab partner can disagree on what you think that estimated value is. But all graduated cylinder measurements that we're going to use in class are going to need to be done to the estimated to the 1/100th. Okay? All right. All right, we use a electronic balance. I tend to call them balances. Balances are really the old ones you might have used in middle school, especially if you're at one of the older middle schools where you had the pan and the pans went back and forth and you put things on it and you move the little rider across. We also call these scales, electronic scales. Okay, what you're actually measuring is weight in this case and not mass. It's how much it's pushing down onto the pan, but it works. The last digit is the estimated digit. So this one is accurate to 1/100th. For volume of liquid, we're going to use the graduated cylinder. I already explained all that. Your uncertainty would be to graduated cylinder that has a precision. Actually, you know what? This guy we read as 1, so he would be accurate to 1/100th. But this guy here, well, it's actually not listed. The ones that you have in class go up by tens, which means your precision is 1 milliliter, and you can read it to 1/100th of a milliliter. Volume displacement was covered last week. The meniscus is the curve of a liquid. It curves because water is sticky. This is one of the reasons that water domes up. If you have a little drop of water, the water sticks to itself, and in a graduated cylinder, it likes to stick to the glass and creep up the side. And that is what the meniscus is. All right, so we have some examples here. We're going to practice reading these. These are all going to, first we're going to determine how much accuracy we need. Here we have 3 milliliters, we have 4 milliliters. It's divided into 1/10. So we know that we can accurately describe it to 1/10. It's between 3 and 4, so I'm going to start with 3. It's between 1/10 and 2/10, 3.1. Now you have to come up with what you think that is. When all else fails, go 5. It's about halfway. The next one, it's between 2 and 3, so we know it's 2 point something. It's between 9 and 10, so we could go 2.99 if you want to, 2.95. Our third one's between 4 and 5. To me, that looks like it's right on the 1. I would call that 4.10, but you might call it 4.11 or 4.09. The last one is between 0 and 1, 0.567. It's between 7 and 8. I'm going to just go with 5. Now, the one thing I didn't do on any of these was put milliliters down. You always have to put your units down. All right. Here's some more work with why significant figures are important. Here's a ruler. This ruler is measured in decimeters, or it's measured by tenths. So we have 1 centimeter and we have 10 centimeters. It's measured in centimeters, not decimeters. Duh. So we have to figure out, we know that it's most accurate to the tenths value. So that means we're going to estimate the ones place. Now you could go through and go, okay, that's 5, and that would be about 2.5. So you could say that this is maybe 3 centimeters. Remember, tenths is what we can accurately measure to. So we know that it's 0 because it's between 0 and 10. We can say that that's 3 centimeters. All right. The next block is measured in 1 centimeters. So this is 1, 2, 3. We know we're between 3 and 4. So we can accurately read to the 1 centimeter, and now we can estimate between 3 and 4. I'll go 3.2. Okay. This same line here, now we have 1/10. So we can read it accurately to 1/10 and estimate to 1/100th. It's between 3 and 4. It looks like to me it's right on the 2, and I'm going to call it 3.20. All right. If we look at the kids in the class, Susan and Maya, both of those answers could be correct because those are both estimated. Jonah went too far. He can't estimate to 1/2 because it's not precise enough. Tony went too far. Emily, you can't use fractions. Get over the fractions, people. And Diane went too far. Dion, excuse me. The second one, Susan, Maya, and Jonah all have legitimate measurements. Tony needs a 0.0 or a point something in order for his to be legitimate. If he had written 3.0, that would work. You and I can look at that and go, it's probably not 3.0, but if that's what he'd written, that's his estimation, it's okay. Emily and Dion, again, trying to be too specific. Here, 3.20 is what we wrote. That's what Maya got. Jonah said 3.22, though. Susan said 3.21. What's wrong with her value? Yeah, she didn't put centimeters down. Mark's not precise enough. And Emily and Dion, again, are just getting a little bit excited about their precision. All right. Now let's say we have a rock. We put it on the first balance. This is the economy balance. This is the good balance, this is the balance pro, and this is the exacto balance. Okay? What is our precision on this balance? It would be the 1/100th area, right? You cannot get any more precise than that. We know that because our exacto balance, we know that it's between 100 and 200. Our good balance says 140, so our good balance, this is to the 100th place, this is to tenths, this would be good to the ones, and this would be good to 1/10. Okay? Same story here. Now, notice, this guy, we're at econo balance again, he's good to the 100ths, but he's closer to 200 than 100, so we round up. When we go to our next balance, we're accurate to the tens place, so we can say 180. The balance pro is actually below that, 177. The exacto balance, 177.1, so it's accurate to 1/10 of a position. All right, now let's look at smaller balances. Here we have a pebble that reads 0. Okay, he's accurate to the ones. This guy is accurate to 1/10, and remember balances are going to estimate the last digit. So he's accurate to 1/10, so you can go to 1/100th, the reading goes to 1/100th. And this guy is going to be accurate to 1/100th, and then the balance estimates to 1/1000th. Okay, same story here. Here we're accurate to the ones place. Here we're accurate to 1/10, and here we're accurate to 1/100th with an estimation on to 1/1000th. All right, let's stop here for now. You have an assignment. to work on metric conversions. Do I have that in here? Some quick metric conversions. If I tell you that I want you to run 1,000 meters, how many kilometers is that? Well, if we do King Henry died, I'm going to use U for unit. King Henry died unusually drinking chocolate milk. To go from meter to kilometer, we move the decimal 1, 2, 3 to the left. So we go 1, 2, 3, 1,000 meters equals 1 kilometer. Okay? If I tell you I have 3.25 millimeters and I want to know how many kilometers that is, I'm going to start at millimeters. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0.00000325 kilometers. Okay? It's just moving the decimals back and forth. Now you have that page that has this at the bottom, so you can use this. All right, if you're starting with micro and you want to go to mega, that's a step of 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. So to go from micro to mega, you're going to move a decimal point 12 to the left. If you're going to go giga to hecto, you're going to move it 3, 6, 7 to the right. Okay? So you guys work on that worksheet, and that's your homework.